Hello everyone, welcome back. In this particular video, we will be discussing the problem, find the equal partition index. Partitioning an array means to split an array along an element and such that it divides the array into two parts with some specific property. So we are saying, the question is saying actually that we have to partition an array into two parts such that the two parts have some specific property. And what is that property known as? First of all, the element which partitions the array is called as the partitioning element. The element which we are using to break the array into two parts, that element we are calling it as partitioned element or partitioning element. So given an array, find the element partitioning along which the property is sum of elements to its left should equal to the sum of elements to its right. The partitioned element itself is to be excluded from both the sums. Return the index of the partitioned element. So we have to find such an index or such an element along which if we divide the array in two parts, all the elements in the left segment should have the sum equal to the all elements in the right segment or in the right side of the partitioned element. And if there is no such element where we can have this property, then we have to print -1. So if I take an example, let's take a bigger array, or maybe let's first take the sample array itself, which is having 4 elements, and the elements are 1, 4, 2, 5. So what is the partitioned element, or what should be the answer? If this is 0th index, first index, second index, third index. If I partition my array along with 0th index, so what will be the left sum? Left sum does not have any element, so it should be considered 0. What will be the right sum? Right sum will be 4 plus 2 plus 5, all the sum of values. So it will be 11. 0 is not equal to 11. So 0th index is not the partition index. But what about first index? Can first index be the partition? Let's try. Let's try to partition the array along the first index. That is, all the elements in the left side will have some 1. All the elements in the right side will have some 7. Again, not equal. Let's try to partition our array along the second index. So if I partition along second index, left sum will be 1 plus 4, 5. Right sum will be also be 5. So 5 is equal to 5. Hence, the second index is the answer. Although second index contains value second, but we have to print the index. In the question, it is clearly mentioned that print the partitioning index, not the value. So we can just print 2 in this case. However, if I would have taken the array, let's say, maybe if I'm giving you the array 1, 2, 3, 4. In this case, will there be any partitioning index or will there be any element where if we partition all the sum of left will be equal to right? For this, what will be the sum of left? 0. What will be sum of right? 2 plus 3 plus 4. Obviously, it will not be equal to 0. 2 plus 3 will be 5. 5 plus 4 will be 9. 0 is not equal to 9. If I partition along the first index, sum of left will be 1, which will not be equal to 7. If I partition along this index, left sum will be 3, right sum will be 4, again not equal. If I partition along 4, left sum will be, you can say 6, right sum will be 0. 6 is not equal to 0. So since there is no such index where I can partition such that the property holds true, we can say answer will be -1, the corner case. So we have to handle the corner case too, but that we can figure out later on. First main thing is how we will solve the normal test cases. For that, if I take an array maybe 2, 1, 4, then let's take 6, then let's take 5, then let's take maybe 10, then let's take 3. If this is the array given to us, we need to find the partitioning index, such an index where the sum of left elements is equal to sum of right elements. And in order to solve it, one of the approaches, one of the brute force solution, which I can think at least is, let's just do what is asked. What we will say is, let's try to partition along 0th index. Let's find the sum in the left portion. Let's find the sum in the right portion. So I will run a loop from 0 till the current index along which I am partitioning. Let's say it is I. So I will run the loop from 0 to I minus 1. And second loop I will run is from I plus 1 till the last index, till n minus 1th index. I will check whether the left sum is equal to right sum. If it is, I is the answer. The current index is the answer. If not, then let's try for the next index. That is I index will get plus plus. I will try I as 1. I will calculate left sum. I will calculate right sum. Check whether they are equal or not. If not, try the next sum. So what will this brute force solution be? It will be a nested loops kind of approach where first loop will be to find every partition index or check for every element whether it is a valid partition index or not. And how to check it? We will require inner loop. that is left sum and right sum. So it will overall be of 2 loops, or you can say 3 loops, but one inside there will be one outer loop, and inside that outer loop there will be 2 inner loops, one after the other. So overall time complexity we can say will be n square only. And since in n square, we can say the time will be quadratic. What about space? In this approach, we are just going to run a loop on the input array itself. No extra space as such will be required. So constant extra space, no extra space as such. But is this the most optimized solution? Obviously, this is very good in terms of space, but can we do better in terms of time complexity? And the answer is yes. But at what cost? There will be a trade-off. If we want to reduce the time complexity, we have to increase the space complexity. We have to take some extra space. So see, I will just give you an idea that how we can actually get to the solution, or how we can think of it. If I'm, let's say, calculating the left sum for 4th index, or maybe let's try for 6th index, what will be the sum? It will be 2 plus 1 plus 4 plus 6 plus 5 plus 10. If I will calculate the left sum for the 5th index, it will be 2 plus 1 plus 4 plus 6 plus 5. If I calculate the left sum for 4th index, it will be 2 plus 1 plus 4 plus 6. So can you see some elements, some are being repeated? If I already know the sum, let's say for 4th index, that is 2 plus 1 plus 4 plus 6. What it is? It is 3 plus 4, you can say 7, 7 plus 6 is 13. Can I just use this 13 sum to calculate the sum for 5th index? That is left sum for 5th index. Left sum for 5th index will be 2 plus 4 plus 1, 2 plus 1 plus 4 plus 6 plus 5. And already I have the sum for 2 plus 1 plus 4 plus 6, which is 13. So just use it and add the new element, which is 5. Similarly, for the blue sum, or you can say for the 6th index, left sum will be the sum of all these elements, that is the yellow elements, plus the new element at the 5th index. So it will be nothing but all the sum of these elements are nothing but this 13 plus 5, which is 18, which we have already calculated, if we have already calculated and stored it somewhere, plus the new element 10, which will come out to be 28. So what are we actually going to do? Just use the previous sum to calculate the new sum. If I know the sum of the subarray 0 to I can calculate the sum of the subarray 0 to I plus 1. If I know the subarray of sum 0 to I plus 1, I can calculate the subarray sum for 0 till I plus 2. And what are these subarrays known as when they are starting from 0th index? They are known as prefix subarrays or prefix arrays. So what we are going to do is we are going to create a prefix array. Not only prefix, but same thing we have to do for suffix, because we don't only need the left sum, but for every element we need the right sum also. So first, let me just quickly create a left sum array, or you can say a prefix sum array. What will prefix sum array store? It will store all the left sum for all the values. So 0th index will store all the sum of the elements till 0th index. What is that sum? We can say it will be 0. 0th index value only, that is 2 only. At 1st index, sum of all these values, 2 plus 1. So for now, you can say array of 0 plus array of 1, which is 3. But actually, if I just say it will be 2 plus 1, that is this value plus this value. Both are same. Either you can add these two or you can add these two. Both are same. But now, when you want to calculate the subarray sum from 0 to 2, you don't need to again calculate 2 plus 1. You already have the answer 2 plus 1 stored here. That is at prefix of I, prefix of 1. So in order to calculate prefix of I plus 1, or you can say prefix of 2, you can just say, take this value plus the new value and store it here. 3 plus 4, it will be 7. And this is correct also. 2 plus 1 is 3, 3 plus 4 is 7. Next, 7 plus new value 6 will be 13. Don't calculate 2 plus 4, 1 plus 4 again. Then again for 5, don't calculate 2 plus 1 plus 4 plus 6 again. They are already calculated, stored at 13. So just use this value 13 plus 5, 18 is the new value. 18 plus 10, 28 is the new value. 28 plus 3, 31 is the new value. So these are the prefix array, or you can say the prefix sums stored in a single 1D array. Same thing we are going to do for the suffix array. So if I just quickly draw the suffix array, let me just make this prefix array a little bit downwards. And let's now do it for suffix. What will be suffix? The right sum array, that is starting from the right side. We will calculate the sum for each index. What is the sum of all elements in the right side of it? For this index, sum of elements in the right side. So if I, let's say, want to calculate the suffix sum for 2, second index, it will be 6 plus 5 plus 10 plus 3. So which sum can I use? Can I say if I already know the sum for second index, which is 5 plus 10 plus 3, just take this value and add it? Yes. So this time we have to travel from right side, not from left side. So we will travel in the reverse direction. Initially, when there is only one element, what will be the suffix sum? In the right side, it will be only 3. Although you might say for sixth index, the right sum should be 0. But for now, we are including the current element. Although in the question, it is mentioned that whenever we are partitioning, don't include the partitioned element in both the sums. Exclude it in both the sums. But for now, let's see what will happen even if we include it. So for now, we are directly taking 3. 3 plus 10 will be 13. Now 13 plus 5 will be 18. 18 plus 6 will be 24. 24 plus 4 will be 28. 28 plus 1 will be 29. 29 plus 2 will be 31. So these are the suffix arrays, and we have just traveled in the reverse direction. So what will be the time complexity to calculate the prefix array and the suffix array? As you can see, a simple loop on the 1D array. So what is the formula? Prefix of I is nothing but the previous value of prefix, that is prefix of I minus 1, or you can also write prefix of I plus 1 is equals to prefix of I plus the same array ith index. If I just show you 1 plus previous value of prefix, 2 plus 1. 4 plus prefix value of previous index, 3 plus 4. 6 plus 7, 13. 13 plus 5, 18. So take the previous prefix value and the current array value and store it in the new prefix value. What will be the formula for suffix? For suffix, it will be, instead of suffix of I minus 1, we will say suffix of I plus 1. For fifth index, we are taking the value from sixth index. For fourth index, we are taking the value from fifth index. So suffix of I will be suffix of I plus 1 plus the current array value. But there will be a corner case. If I will say for 0th index, what is the sum? If I will take array of I, that is good. But what is prefix of array of I minus 1 or prefix of I minus 1 actually? 0 minus 1 is minus 1 index. We should take the value 0 in that case. There is no minus 1 index. Similarly, for this index, what will be suffix of I plus 1? There is no suffix of I plus 1. There is no 7th index. In that case also we have to take 0. So we have to take care of the corner case where suffix of I plus 1 does not exist. Or you can say I plus 1 is out of the range. Similarly, if prefix of I minus 1 does not exist, or you can say it is out of the range, we have to take them 0 because empty array is 0. Now, once we have created both of these arrays, that is the prefix array, the suffix array, how we can use both of these arrays in order to check which element can be as a partitioned element. See, if I take this fourth index for your observation, can you say that the suffix value is equal to prefix value? 18 is equal to 18. Now, what is 18? This value 18 is 2 plus 4 plus 6 plus 5. This 18 is nothing but 5 plus 10 plus 3. Prefix is nothing but sum of all elements in the left, including the element. Right now we have included it. Suffix is nothing but sum of all elements in the right, including the element. Although for partition, what should be the condition? 2 plus 4 plus 6 plus 1 should be equal to 10 plus 3. Are they equal? Yes, 2 plus 1 is 3, 3 plus 4 is 7, 7 plus 6 is nothing but 13. This is also 13. 18 is equals to 18, 13 is equals to 13. Why? Because if I am saying in this array, in the left sum, if I will add the current element, similarly, if I will add the current element in the right sum, it will have no effect. If I am saying left sum is equals to right sum, the left sum plus the current value val will be equal to right sum plus current value val. I am just adding the current value in both the arrays, in both the sums. 5 is added in the left, 5 is added in the right. 13 plus 5 is 18. 13 plus 5 is 18. So we can just include the element also. It will not have any effect in the answer. And including the current element will actually make the job easier. It will make our code easier. Otherwise, we have to compare 13 with 13. That is prefix of I minus 1 with the suffix of I plus 1. Or you can directly compare suffix of I with prefix of I. Directly same index or previous index of prefix with the next index of suffix. You can compare anything. Better will be to compare directly the same indices, because including the current element in both the subarrays or in both the prefix and suffix, in both the left sum and right sum, will not change the logic. And what will be the time complexity for this optimized approach? Calculating the suffix array will be linear. Calculating the prefix array will also be linear. And to check which index is pivot index, which index is partitioning index, just run a loop again and compare both the values, whether they are same or different. If they are same, that is the answer. So that will also take linear time. So overall time complexity will be linear and overall space complexity will also be linear in this case because we are creating two individual 1D arrays. So linear time complexity, linear space complexity will be the optimized solution using prefix and suffix concept. So let's write the instruction manual, that is a pseudo code for this problem in milestone number 3. So what we are going to do is we are going to create two arrays. So first we have to create a prefix array of size same n only, and which is the input array size. Similarly, create a suffix array. And both of these arrays will be, of course, of the same data type as the input. So create long array that is of type long in case of C++ or Java. It will be long. In some other languages, it will be some other data type name, but you have to take 64-bit integers. Then what we have to do is initially all the elements for all the integers or all the indices will have 0 value. Same in the prefix, same in the suffix. We have to store the prefixes sum. For prefix, we have to run the loop from left to right. So run a for loop over indices 0 till n minus 1. And every time what we have to do, just add the current value in the prefix and the previous prefix value. So apply the formula of prefix at I is equal to prefix at I minus 1 plus the array at I value. That is prefix of I will be prefix of I minus 1 plus array of I. But just make sure that if prefix of I minus 1 does not exist, then take it 0. So I am just writing a note here that if prefix at I minus 1 does not exist, or maybe we can simply say if I minus 1 is less than 0 or I is equal to 0, in that case, the I minus 1 will be less than 0. Then what we have to do is then prefix at I minus 1 should be 0. Then we have to take this value as 0. That is, there is no previous prefix array. Same thing we have to do for suffix. But for suffix, we have to run a for loop from the last index over indices n minus 1 till 0. And formula will be suffix at I will be equal to suffix at I plus 1 plus array at I. And same thing that if the suffix does not exist, then we have to take it 0. But in this case, the suffix, when will it not exist? When the index is last index, because for last index, next index will be not there. So suffix at I plus 1, in that case, we have to take them 0. Once we have created both of these arrays, now we can compare whether which index will have the same value for both the prefixes and suffixes. So I will run a loop, run a for loop again over all indices 0 till n minus 1. Check if the prefix is the same as a suffix. If it is, then the index is the answer. Then we can say, if yes, then return the index. Otherwise, if we are not able to find any index, then what is the question saying? What we have to return if there is no partitioning element? We have to return -1. So finally, after the loop is end, there is no partitioning element found, then return -1. So this is the instruction manual, and already discussed the time complexity will be n plus n plus n, that is 3n, which is still linear only. And space complexity, since we are going to create two extra arrays, prefix array, suffix array, we will take linear extra space. So in order to reduce the time complexity from brute force n square to optimized n, we have to take extra space of linear. So there is a trade-off. And with that, we are done with the first part. For the particular video, we will be writing the code in Java programming language. So let's just directly use the instruction manual in order to write the code. First thing, what we need is to create a long prefix array. So long array of prefixes, and the array size will be n. Same thing we have to do for suffix. So let's just first create the same array for suffix. And for now, what we are going to do is we are going to fill the values for prefix by running the loop in left to right order. That is, indices will run from 0 till less than n or 0 till n minus 1. And every time formula will be prefix of I is nothing but array of I plus prefix of I minus 1. Prefix of I will be nothing but prefix of I minus 1 plus array of I. But the note is, if the index I is 0, then prefix of I minus 1 does not exist. It should be taken as 0. So we can just compare whether I is 0 or not. If I is 0, take the value 0. Otherwise, take this value. That is don't go into index out of bound exception. So we are able to take care of the note also. So first, let's just print whether the prefix array is correct or not. So we are going to use arrays dot toString, and I will just pass the prefix array in it. And obviously the prefix array name is pref. We should use the same name everywhere. And for now, let this return -1 so that there is some return type. So let's see whether the prefix array we are creating is being created correctly or not. Although there is some issue with the variable name still, we are using prefix, and the array name is arr. And what is the error? Let's read the error. Cannot find the symbol I. Okay, so ith index is not there, but index name we should have is I. Instead of index, let's just have variable name as I. And let's run it again. So it is taking some time to run, and still there is some issue. The prefix array name is prefix, not prefix, but it is pref, only pref. Let's see now if it is going to show me the correct output for prefix array. So for prefix array, it is giving me 1, 5, 7, 12 for this array. 1, then 1 plus 4, 5, then 1 plus 4 plus 2, that is 7, then 1 plus 4 plus 2 plus 5, that is 12. So yeah, prefix array is correct. Same thing, let's just do for the suffix array. So for suffix, let's just have the suffix array name as suff. We will run the loop in reverse order, that is index from n-1 going till 0, index minus minus. And the same thing just in reverse order, that is suffix of I is going to be nothing but suffix of I plus 1, not I minus 1, plus array of I. And now the corner case will be if the index is the last index, that is n-1. In that case, we have to take the value 0. So if index is n-1, take the value 0. Otherwise, take the value of suffix of I plus 1. So I'm using ternary operator to do this. So hopefully it should also be correct. Let's just, for now, print the value of suffix arrays dot toString. Let's just print suffix array to confirm whether this is also correct or not. So again, taking some time to run. And we are getting 12, 11, 7, 5, 5, 5 plus 2, 7, 7 plus 4, 11, and then 11 plus 1, 12. So this is also correct. And finally, let's compare which index have the same value for prefix and suffix. That will be our partitioned index. So I will run a loop for all the indices. I will check which index have the values at prefix array and suffix array equal. So prefix of index, if it is equal to suffix of index, then we have to do what? We have to return that index. But if no such index is found, then we have to return -1. So corner case should be, if there is no partition index, answer is -1. That will also work correctly. So let's submit it to see if all the test cases, including the corner test case, which I just told, is working fine or not. And as you can see, all the test cases are getting passed, even the corner cases. So what is the time complexity of this code? Since we are running a loop for n times, again running a loop for n times, again running a loop for n times, n plus n plus n is 3 times n, but it is still linear. Although if you wish, you can just reduce one number of loops by creating the prefix array after suffix and just comparing while running the prefix array itself. Why? Because when we are running for prefix, we are going from 0 to n-1. When we are running the loop for suffix, we are going from 0 to n-1. So we can just combine these two loops, but still time complexity will be linear only. The code will become a little bit smaller. And what about the space? Since we are taking two extra arrays, prefix and suffix, it is not in the input. The extra space complexity is also linear. So linear time, linear space, optimize the solution. And this is the solution for the problem, find equal partition index. With that, we are done with the video. We will meet in a new video with a new problem. Till then, bye-bye. Take care.